Hello everyone, you're tuned into today's PIR live event and I'm your host Scott Jones. Before we get started, I'd like to welcome our live stream viewers. Remember that you can tweet your questions using hashtag AskPIR anytime during the live event and I will relay them to our guest when it's time for the Q&A. If there's room in your tweet, please include your name, school, or city so we can give you a shout out. I look forward to getting to those questions, but first I'll introduce our guest today, who is Dr. Dave Hayes. Dr. Hayes is formerly a research associate at the University Health Network at the University of Toronto, and he's currently a visiting assistant professor at Union College in Schenectady, New York. Dr. Hayes, thank you so much for joining us today. I'll turn it over to you so you can tell us a bit more about your work.
Hi, thanks for inviting me, Scott. So I am a visiting assistant professor in neuroscience and psychology here in upstate New York. So I do research and I do teaching, and my interests are really focused on emotion and the brain. So in terms of the behavior and the brain. So I'm going to show you some pictures now. I'm going to put up share a presentation with you. There you go. How's that? Can you see that? Perfect.
Yep.
You can? Great. So my interests are on what's called the affective brain or the emotional brain. And up until maybe a couple decades ago, we couldn't really look inside human brains and see what was going on in terms of the structure of the brain or the function of the brain. But ever since the invention of functional neuroimaging and just neuroimaging techniques like the picture that you can see here, we can take a look at the kinds of activity that is happening inside the brain. And also we can look at the structure, so how brains are connected inside. The first thing I wanted to say is that I call it affective neuroscience or effective or instead of emotion. And so what do I mean by affect? Well, there's this thing called affect, and it's really about how the brain processes positive and negative things in the world. So when you walk into a room and you say to yourself, I've never been in this room before, but I don't like it for some reason. That's because your brain is working through all these different things and sort of putting together what it likes and what it doesn't like and coming kind of to a conclusion. And you might not be able to say why you don't like it or why you do like it, but this is sort of your affective brain working things out. But when this takes place, so your reaction to that, like happiness or sadness, that would be called an emotion. So when you get happy, that's an emotion. But it's based on how your brain is sort of functioning, whether it's overall positive or overall negative. And mood is something that would be putting together sort of affect and emotion over a long period of time. So somebody asked you how your mood was today, you'd sort of think back and say, oh, in general, I had a pretty good day. So your mood was pretty positive overall. Or maybe you were really irritable all day, you're really irritated at something. And that doesn't mean you can necessarily put a finger on what it is, but you just feel irritated. So before neuroimaging, the way that we discovered how bits of brain worked, or how the brain worked, was usually from accidents. So there's this one famous example about this guy called Phineas Gage. And unfortunately, he ended up he worked on a railway, and he put explosives into the ground. He helped put explosives into the ground so he could blow up rock and lay room for track. And so Phineas Gage one day was sort of using this big tamping iron thing and sort of tamping down there, or sort of tapping down the bar, and the explosive went off and it went right through his head. You can see a picture of that here. So the bar actually went right through his eye and up through his brain. It took out a piece of his brain. Now the bizarre part about this is that he didn't, well, you might think he would die, but he didn't die. In fact, he was only unconscious for a short period of time. Although he was injured for a while, he actually made a full recovery and he lived for years afterward. The strangest thing about it was that his IQ didn't change, his intelligence didn't change at all. He had the same intelligence, but what happened was that he was unable to control his emotional behavior. So he used to be very, very kind and polite, but instead, after the accident, he became sometimes he would go from being happy to very angry instantly, explosive, and he would just start yelling at people. And he didn't seem to have much patience anymore. And before neuroimaging, we would have no idea why this was. But after we started to use different techniques, looking at research in, for instance, animals and in humans using neuroimaging, we sort of understood that there's a whole bunch of regions in the brain that are sort of networking together or working together in order to create this experience of affect or emotion. And so the region that was important for Phineas Gage was this area called the prefrontal cortex in the front, which is responsible for regulating your emotion, but also helping you make important decisions every day. And so, like I said, one of the important discoveries was the discovery of neuroimaging techniques like magnetic resonance imaging, where we can put people in to this scanner and we can take a look at the inside of your brain when it is working, how it's working, and we can take a look at the structure as well. So this is the kind of stuff. I'll show you some pictures of my own work. So I've been able to look at people's brains when they're working and when they're looking at, for instance, or listening to pleasant or unpleasant stimuli or things. So we can show a picture of like an angry dog, or we can show a picture of a happy baby, and we can take a look at brain function. And although we can't see what it is you're looking at by just looking at your brain, we can tell if you're having a positive or negative experience overall. So that's this map here. So these are the brains and sort of the brain slices here. And the colors represent sort of what these people are experiencing overall. So you can see that there is what we call positive affect. So this is when people are looking at like pleasant pictures or listening to pleasant sounds, like nice music. And then there's this negative affect in blue where people are having, maybe they're looking at spiders or, moldy food or, angry people or something. So we can take a look at what areas of the brain are sort of involved. The other things we can do is we can look at the connections in the brain. So these are models of white matter tracks, or white matter is the way that the brain will connect different areas together. So we can sort of look at the highways of the brain. And these are examples of that. And they have sort of interesting names like the fornix and the cingulum and the medial forebrain bundle, all a mouthful. So this is another example of some of my own work where we've looked at some of these sort of messy highways, and then we've looked at people's reported experiences of unpleasant events that they had in their childhood, for instance. And we're able to sort of compare what's happening in terms of the structure or the function of the brain with what people report. So some people report that they had some unpleasant experiences as a child, and so we can see a little bit of that in the brain. And some people who for instance, report really, really pleasant experiences, sometimes we can see that in the brain as well in terms of the structure and the function. So for instance, when you've got this happy lad right here, he's got chocolate all over his face, that's why he's really, really happy. We can see that if we were to scan his brain, we could see that he's got a sort of happy brain in terms of the networks that are involved. But also we know that if he continues to have a really happy childhood, that will affect the way that his brain is structured, so the wiring, the way that it wires together. Because brains are not sort of static, they're not just sitting there, they're always changing in terms of their function and their structure. They're always rewiring depending on your experiences. So if you want to change your brain, you have to change your environment and change your experience. And then of course you have this as well. Negative emotion is a good thing. Crying babies tell us that they need something, so that's really important. You can't be happy all the time. But if you're really, really unhappy for extended periods of time, that can change your brain in ways that maybe you don't want. So that's why we sort of think of affect or emotion as being really important for a whole bunch of things, such as like everyday well-being and decision making and how we learn and how we memorize things. But also when those circuits aren't working quite right, or when there's something wrong with them, almost like like a broken arm. If you have a broken arm, you're not able to catch a ball, you're not able to play. It's the same way. If your brain is a little bit broken too, you might need some tools to help fix that. And if your brain is broken, you might experience something like depression or anxiety or schizophrenia. There's a whole bunch of things that can change how we experience the world in terms of our emotional experience or our affective experience. So those changes in our brain function and structure, can lead us to actually experience the world in a completely different way. So someone with, for instance, major depressive disorder doesn't experience the world in the same way that you or I might. And I'm going to stop this share, and I'm going to show you something else just out of interest. So as I said, some of the work that I do involves making, here's it, great, involves making these models of the brain. So what we're able to do is we can look at this is a picture of somebody's head and their brain inside, and you can see this is the back of the head back here. I don't know if you can see my cursor, yeah. And then this is the front up here, the eyeball's about right here. And what I've done here is I've been able to model a major tract in the brain. So this is connecting the front of the brain to the back of the brain. And this particular tract here, this tract in yellow, is called the cingulum, and it is involved in carrying a lot of emotional information. And there's this other tract down here, medial forebrain bundle, which is also involved. What we're able to do is see these tracts in 3 dimensions. So it's really nice that, because neuroanatomy or brain anatomy is difficult to understand in 2 dimensions. But you can see here that there's sort of like, you can zoom in and you can see that it has structures, and that it goes not just in one plane, but you can see it go in different planes. And then we can scroll through and see exactly where it's going in the brain and how it's connected. And even though everybody has a cingulum, it will look slightly different depending on who you are and what your experiences are. So I will leave that there, and then I'm happy to take your questions, if you have any.
Okay, great. So that was very interesting. A couple of things that I was wondering was, so you talked about affect and how it might affect, say, our mood throughout the day. Does it also affect our behavior? Like, are we predisposed to certain behaviors based on this, how our brain is structured and wired?
Yeah, so that's a great question. And the answer is absolutely. So there's a lot of variability, and to get what you'll find is that neuroscientists like me who are interested in brain and behavior can give some information, but we're just at the beginning of trying to understand all of these things, and they're really, really complex. So there's a whole host of things that will affect whether or not the circuits that you have, or I should say how the circuits that you have will impact the way that you behave. So for instance, some people are said to have a little bit more resiliency. And you can even, and so what that means is that some people will be a little bit more, they'll respond differently to challenges like stress in their life. And that does have a lot to do with sort of the structure of your brain, the circuits that are existing. But that's not to confuse the idea that I don't want to give anybody the impression that you can't blame things on your brain, because in essence you are your brain, but you're also responsible, just like the rest of your body. The rest of if you want to be physically healthy, you go to the gym, or you do some running, you do some playing, you make sure that you stay physically active, and so that helps build your muscle, and also your muscles, and helps you helps your heart function better. But in the same way, we have to be responsible for mental health to some degree as well. So we have to make sure that we do things like go to school, we keep thinking and keep challenging ourselves, but also the physical and the mental interact. So we have to make sure that we keep exercising, because we get lots of blood flow, good healthy blood flow to our brain, make sure that it's staying really healthy. And so it's these kinds of things that can alter the circuits one way or another, and then ultimately they'll impact how we respond to stressors, or to frightening experiences in our lives. Everybody experiences stress, that's a normal thing, but some people who experience stressors seem to be bogged down a little bit more by them, or they feel like they're trapped, or they feel like some people report the feeling of being in quicksand as soon as they get a stressor. So if something unpleasant happens in their life, like they get an F in a course, and they think, oh, this is it, this is the end, this is awful, But other people say, okay, I got an F, but I'm going to turn things around. And that has a lot to do with how your brain is structured and how it's functioning. But you're not trapped by that. Your brain is always changing. So you can change, how you think about things, and you can change the structure and function of your brain by, as I said, doing a lot of things like talking to people, learning about how you can change those things and how you can change your behavior. And doing things like making sure you're staying healthy, eating right, exercising. They all change brain function and structure.
Right. So obviously, though, it's during the period of the brain's most intense growth, like when we're infants, is when the brain undergoes the most growth.
Right.
So does that still bias the way we are as adults? And if so, what are the timelines on changing these patterns that may have developed at that time?
Yeah, it's a great question. So the answers used to be, not that long ago, maybe a decade or two ago, used to be that there was they were called critical periods, and those critical periods really determined in the first few years really determined what language you would speak and how you would behave and what sorts of things you would experience and what sorts of things you wouldn't. And they were called critical periods. But that view has changed quite a bit. We know that the early days and early years are really, really important, like absolutely fundamental. But now it seems that there's so much variability and so many ways to change things over time that we now refer to them more as sensitive periods. So, for instance, to give you an example not related to emotion, but language, for instance. I'm not a language specialist, but I know that it used to be considered, we put hard dates in terms of, this many, 6 months to 12 months are really fundamental for, hearing certain languages. If you don't hear German in the first, 12 months, you're going to have a very, very difficult time, learning how to speak with a German accent later on. But actually that's changed quite a bit. So it's still true that if you're not exposed to German in the first 12 months, that some of the recognition of the sounds sort of goes away, or it's not recognized by children as well. But that doesn't mean we can't learn the language. And in fact, we know that if you learn sort of other languages before the age of, say, 12 or 13, you can be perfectly fluent as though you're a native speaker. Whereas as you get older, it becomes harder to do so, but not impossible, just harder to do so. So all that is to say, when we start looking at emotion, which is what we've been doing in the last couple decades, we've really started to understand that, yeah, exactly, in the first few years of life, particularly in the first 10 years, what we experience really plays a role in how we will respond to stimuli as an adult. So, for instance, if you have if you live in a neighborhood that's, quite dangerous, you will learn to expect danger in your environment, so you'll be really vigilant, you'll be really aware all the time of potential dangers, whereas somebody else might not be. And that makes sense, I think, for most people behaviorally. But in terms of brain structure, we can actually, and function, we can actually see some of that. We can see that the networks in the brain associated with being aware, really vigilant, really aware of sort of fearful things or dangerous things, we can see that they're more active in those kinds of people. And in a way, that's not a bad thing, because if that's your experience as a child, you want to be able to adapt as you grow older, and you should have that expectation, in a sense, that your childhood environment will be the same or similar as an adult, even if it's not. So it can be detrimental if things change for people. For instance, if they had they lived somewhere that was dangerous or frightening for a year, but then later on they're in a quite safe environment, but they can still respond as though things are very fearful. So for some people, it could be the trigger of, taking a test. You could get test anxiety. It's not associated with your environment as a child, but yet the circuitry in your brain has been sort of molded to sort of expect that little things could be potentially big, dangerous things. So people might respond differently. That said, though, there's still a lot of variability, even in all people who are raised in like one similar neighborhood, which might be dangerous. We still see a lot of variability. So some people might get post-traumatic stress disorder or anxiety disorders, whereas other people don't ever seem to develop that. And so we're still trying to figure out why that is. Even before people are born, actually, there's some evidence now, both in animals like rats, but also in humans, that the experience, the stress levels that a mother experiences can be somewhat, I don't want to say passed on because that's not true, but can be somewhat somewhat passed on, it's not quite right, but somewhat passed on or somewhat experienced by the unborn baby. So when the baby comes out, so because that stress that the mother experiences is helping to wire the baby's brain. So again, it's not necessarily a bad thing, because if you're in stressful experiences, if you have a stressful environment, you want to be prepared for that. So you want a brain that can be a little bit more resilient to that stress and a little bit more prepared for that. But again, there's a lot of variability, and we're still trying to work things out. My own, I showed you that one picture from my own work showing that we just asked adults. We didn't know about their actual childhood experience, but we asked adults to think back and report different experiences. So think questions like, when you were young, did you have enough food to eat regularly? Did anybody in your life regularly hit you? Those kinds of things. And what we found is that there were relationships or correlations to what we could see structurally and functionally within those people's brains. And that was just them thinking back and reporting. There are other studies following people from childhood that also show similar results.
Okay, that's very interesting. We have a couple of questions coming in. One from Innisfree, Alberta. And this comes from Tamara and Anne, who both want to know, why do people like different food? Does that have something to do with the brain?
Yeah, it's a great question, Tamara and Anne. So again, a really complicated answer, and we don't fully know the complete answer, but I can give you snippets of what we do know. So food is interesting because it's considered a primary reward. And what that means is that when babies come out, they don't have to learn that food is good. They immediately experience food as being rewarding. So that is kind of interesting in and of itself. It sounds maybe like it would be intuitive for most people, but actually it's kind of weird because babies have never tasted anything before the minute they pop out and they go and have some milk. They've never tasted anything because the way they're fed is, through a tube in the belly button, right? So you don't actually nothing is actually working. They're not, they're not eating steak in the belly or anything. So when they pop out, it's immediately rewarding. So brains are pre-wired to do certain things like want food and want to eat food, even if they've never experienced it. And we're also pre-wired to want things that are like sweet. So we like sugars because sugar is fuel for our brain. And water, because water is fuel for our brain. So we already have a predisposition to liking sort of things that will give us nutrients in terms of food. But then the question is, why does someone like macaroni and cheese and someone else hates it? This is why would that be if we're predisposed to like food? And the answer is because as we sort of have our experiences in the world, we're changing those brain circuits all the time. We're changing how our brains function. And so different people create different associations or have different associations with food, different experiences. So some people might like macaroni and cheese because, it's got fat, that's good fuel. It's got sugar, that's good fuel for our brains and our bodies. But they also probably experience, I'm hungry, it's tasty, cheese is good, whereas other people might be a little bit lactose intolerant, for instance. And even though you might not be called lactose intolerant, some children, really young children, will have the experience, without adults even knowing, will have the experience that they have macaroni and cheese, and then maybe they don't feel as well as the person who loves macaroni and cheese. They still might like it in the beginning, but maybe they feel a little bit queasy. They don't know why. And it's because they might be a little bit lactose intolerant. And that experience over time will have those children thinking, I don't like macaroni and cheese anymore. So they don't know that they're lactose intolerant. And in fact, they may never be lactose intolerant enough to to like not have a glass of milk. They might not have a huge reaction. Just a little bit is enough to sort of give an experience over time. So that's just one example. But there are lots of other examples. If you gave someone, had people eating, an apple or something on one day, and then all of a sudden something terrible happened, like maybe say an earthquake, which frightened a young child, 3 or 4 years old. They didn't understand it. They might actually pair that in their brain with eating an apple. And even though it seems sort of illogical and silly, that could possibly happen. And so in the future, when someone says, would you like an apple? They don't remember that the earthquake happened at the same time, but they would say, oh no, I don't want an apple. And if you ask them why, they say, I just don't like apples. So there's a whole bunch of little things that's a big thing, but there are a whole bunch of little things that can happen as well. How you're feeling at the time when you eat that food for the first time or for the second time can play a big role as well. Like I said, you've got that affective circuit, an affective brain function happening all the time. So overall, if you think about right now how you feel, you could probably say, you think about it for a second, you go, okay, I feel okay today. I feel pretty good. Or maybe I don't feel well. Maybe I woke up this morning and I was unhappy. I don't know why. That just happens. It happens to everybody. But that can actually impact how you experience everything, and including food. So that's sort of a part example or a part explanation. But there are lots of things we don't know in terms of why people have these subjective differences. And that's something that's really interesting to us.
Okay, very good. Can you tell us a bit more about the kind of the experimental aspects of your work? So you showed us the image of the different parts of the brain lighting up when you're talking about different, or bringing up different subjects. But how exactly are you able to control for the subjects, thought processes? Like, maybe they're preoccupied while they're taking their test and they're thinking about something that happened before they came in or something. How are you able to control for that?
Yeah, that's a great question. In many ways, we're not, because obviously when you put somebody in a scanner or at any time of the day, even when sitting down watching a television program, sometimes our minds wander. Even when we're having a conversation with someone, sometimes our minds wander, and then we find almost a few seconds later, oh, I wasn't paying attention there. It's almost like you're not aware that you're not paying attention, but you might have been thinking about, what you're going to eat for lunch or what you're going to do tomorrow, these kinds of things. So it's difficult to control completely, but we often have conditions where we think of those kinds of things, the mind wandering, we think of those kinds of things as being relatively random. So it'll be interspersed randomly across people, and as long as we have sort of proper control conditions, we can help to separate out our effect from sort of a non-effect. So an example of that would be this. I could put you in a scanner. We don't want you to move a lot because the scanner is taking a picture of your brain. So just like in taking a picture with your camera, if people are running around and you don't have a high shutter speed or something, you're not going to get a very clear picture. It's going to be fuzzy. So we don't want people to move their head. But what we can do is we can show them pictures. So I can show people really pleasant pictures that make them sort of smile or make them sort of happy to see. Nice things like some people like, the beach or, laughing children or, nice fancy cars or, someone sailing or something. And then that you'll experience overall, all those pictures you'll experience a pleasant you'll have a pleasant experience. But then we would also use other pictures to contrast, and we would use pictures that are unpleasant. So as I said before, like spiders or moldy food or angry faces. But we would also use neutral items like looking at a chair or looking at a desk or things that most people don't have too much of an effective response to. They don't feel positively or negatively overall. And we would show lots of those pictures, and then we're able to contrast all the times that you saw happy things or nice things, and all the times that you saw sort of neutral or uninteresting things. And then we can look at the brain activity there. And when we do that across people, what we see is similar brain areas, similar networks popping out. So that's one way to control for it. We also do things that we'll look at people's, we can watch where your eyeballs are. We can see exactly where your eyes are tracked, so we can see that you're looking at the picture and that you're engaged. We can ask people to respond in the scanner, so we give them a little control panel, and they can just move their fingers to say, A, B, or C. and we can ask them questions. And we can also look at some of their physiological responses, like your heart rate, your breathing, and even your what's called galvanic skin response, which is kind of the electricity in your skin. And that electricity in your skin actually changes with the experience of strong affect. So you might have noticed when you're afraid of something, or when something's sort of spooky, the hair on your arm will stand up and you sort of get this tingly feeling. And so you at that level, you can actually feel sort of the electricity in your skin. But at levels where you can't even experience it, if we put an electrode on your skin, we can actually see those little changes. So there are a bunch of ways that we try to sort of control for things. But as I said, there's a lot of variability. So we can only do so many things.
Okay. Quickly pop back to Twitter here. A question from Donovan, who wants to know a bit more about Phineas Gage and how Gage didn't die from the pole through his head. He thought that when your brain was touched or pierced, you instantly died.
That's a great question, Donovan. So no, you don't instantly die when your brain is touched or pierced. In fact, there are lots and lots and lots of case studies showing, this is individual sort of examples throughout time, showing that if you touch brain areas or you lose brain areas, that they don't always cause death, and in fact they don't even cause, sometimes they cause huge changes in terms of behavior, but sometimes they cause changes that are so subtle most people don't even know. So I'll give you a couple examples. In war times past, there are examples where people will experience injuries which are really unfortunate, some of which would be pieces of their skull missing. It's kind of horrific. But physicians at that time, or surgeons right on the battlefield, would try to help. And what they would find early on, they would report that sometimes when they tried to patch things up in the skull, so people would still be alive and doing well, bleeding a little bit obviously, but doing well. If you could stop the blood, they would live. But the surgeons noted that when they touched the head, sometimes, especially if you touch the right side of the head, for instance, sometimes their left arm would move like this. And the patient would say, I don't know why that happened. So it turns out that there's a strip of cortex or brain area on the right side that controls the left side of your body in terms of the motor function. So if you touch certain areas up here, actually physically touch them, you can get your arm or your leg to move on the opposite side of your body. And now we have actually techniques where we can use, one's called transcranial magnetic stimulation, where we're using a little handheld magnet, and we can place it over the motor cortex or anywhere on the brain, and we can stimulate that region. We can sort of shut it down or make it a little bit more active. And what we can do is we can make your arm move, even though you didn't want it to. So the people this happens to, they sort of laugh because it's weird to have your arm move when you didn't tell it to. So that can happen. But there are lots of other examples too. So one other interesting example is that there's an area of the brain called the corpus callosum, which connects the two hemispheres. So the brain actually comes in two hemispheres. If you want to know how big your brain is, by the way, you put your two hands together like this, put your two fists together. That's how big your brain is, the two fists. It's maybe not as big as you'd like it to be, but it does its job. But the two hemispheres are connected by a white matter tract, a white matter highway, and it's called the corpus callosum. And in some people, the corpus callosum is cut by surgeons because it helps with, for instance, it can help with some dramatic examples of seizures. But anyway, when they thought, in the beginning, the surgeons thought, okay, we're going to do this because these people, their lives are very difficult. They're not able to walk around. They're having seizures all the time. They can't work. They can't play. So they tried this radical surgery, and they thought there would be this huge change in maybe their behavior. But they had no other choice. It was really radical surgery. But as it turned out, people got up. The two hemispheres were cut in half, but they got out, and they were perfectly fine. No IQ changes. Most of them, you couldn't even tell that they'd had this major brain surgery. And there are reasons for that. It took researchers to discover that actually there are changes, but in your everyday life, people sort of compensated for them, and so you couldn't tell based on their behavior, even though their two hemispheres were having a hard time communicating with each other, which did change how the brain functioned, but it was hard for people to see that. So there are lots of examples like that. You don't need all of your brain to live, but if you miss a part of your brain or you lose a part of your brain, then it can have dramatic effects on behavior.
Right. Okay, we're a little bit over on time here, but maybe I'll leave you with one more question just before we sign off. And this comes from Innisfree again, Mrs. Sasha, who thinks that student anxiety has increased. And because of this, has the teen brain changed?
Has it changed? Right. It's not actually an easy question. It's a difficult question, I think. And the reason is because we haven't always considered mental health. Historically, we haven't always considered mental health like we do now. It used to be, now we think of it like, if you've got a broken arm, you would never have been expected to play on the baseball team. It's okay to sit out while your arm heals. But in terms of brain function and mental health, people were just always told, even people in sports that had major head injuries or concussions, you'd just be expected to go back out on the ice or go back out on the field and play because you couldn't see the damage, so most people just assumed it wasn't there. So in terms of that, anxiety wasn't an issue to be reported in the past, although there are lots of examples of where, obviously anxiety existed, but it was often kept quiet. People would have shame around it, whereas now it's different. So now it's considered something, at least it's getting there. It's might not be completely where we would like to see it, but it's getting to the point where people will report that I'm having a lot of anxiety and, I want to try and deal with that. It's impacting my life and I would like to try and change that in positive ways. So we see more reports. So we're not entirely sure that it's that we're getting more of it than we used to necessarily. It's just being reported more frequently, and we have better strategies to deal with it than we used to. But in terms of the teenage brain, is it changing? I mean, yes, and it must be in some ways, but we're not sure how meaningful it is. So the internet didn't exist when I was born, and I didn't have that in school. I couldn't Google anything because Google didn't exist. But now we all Google. Now we all use the internet. Now we, at least at some point in our lives, we use smartphones. We're connected. We don't wait for TV programs. We can just turn on the internet and go to YouTube and find any TV program that we like. These kinds of things. So, in a way, our brains are fundamentally changing. They're different than what they would have been before. But we're not really sure if that's leading to changes in anxiety, and we're not really sure if those changes that we see are bad or good. My guess is probably neither bad or good, because things are often set up as though, is this bad? Are video games bad or are they good? And the answer in my experience is almost always, it depends. It depends what video games you're playing, it depends how often you're playing them, it depends on, a bunch of things. What kind of person you are already, how your brain is functioning already, how much exercise you're getting, what you're eating, what your environment is like, all those kinds of things. So, is the brain changing is a great question. I think it's changed. There's evidence that it's changed, obviously, over history, like very long history, because brains have evolved. But we're not sure if these kinds of things like the internet and constant connection is a hindrance to sort of brain structure and function. Some people have suggested that because we have this all the time, where we used to have downtime and quiet time, now we're always connected. Some people have suggested that perhaps brains haven't evolved sort of fast enough to keep up with it, and so there's a bit of friction between the sort of the fact that we're always on and we're always able to connect, and our brains can't keep up with that, so that may result in anxiety. And I don't think there's a clear answer to that yet. It's an interesting question. But I don't think we know. But I do think that the answer is probably it depends on individual circumstances.
All right, good. So unfortunately, I think we're fresh out of time for today. So I'd like to say thank you to our live stream viewers, and of course to you, Dr. Hayes, for taking the time to share your expertise with us and answer all of our questions. So thank you so much.
Thank you.
I'll just do a quick plug for our next event, which is next week, Thursday, March 24th. We'll learn about the factors that affect our ability to regulate body weight, and then we'll get a peek into the next lab and see the equipment that Dr. Nick Bellissimo uses at Ryerson University for fitness tests and body composition analysis. So that will be something to look forward to next week. In the meantime, thank you again, everyone. Thank you, Dr. Hayes.